and then get rid of dot like square. Is that good?
Yes, we can hear you. Can you still hear me?
Yes.
Audio okay? You see the screen? Okay, please, everything's fine. Go ahead, please.
Okay, good. Well, thank you. This has been good. I've been listening all through. Great presentations and good opportunities going on in Texas. I thank you for this opportunity for me to speak, and I do apologize for not being able to travel to Texas. I will take that invitation in the future if that all works out again. And if you like my presentation, that would help too, I guess. I'm going to be speaking about nutrient delivery systems. And I say as an engineer, the fun parts of plumbing and pumping water around. And that's why I asked the question right off the top, why a nutrient delivery system? Why is that my topic? Well, Genoa spoke a lot about environment in the aerial portion of the greenhouse. This is looking towards the root zone and the challenges of providing water as well as the nutrition to the plants through the roots as they expect them to be provided. But also the nutrient delivery system can be many things to different people, particularly the growers, depending on their choice and how that they put them together into their growing system. And that will depend on the crop that they're growing. The first consideration should be, what crop am I going to grow? How do I know how to grow it? What is my best experience with a nutrient delivery system, a hydroponic system, basically, in a controlled environment? Because taken together, the nutrient delivery with which controls the root zone, and the aerial environment, which is controlled by the fundamental heating, cooling, environmental control, and then the hands-on plant care, that is the green thumb. How do I manage this plant physically and environmentally? Those three things are critical to success of your crop, obviously. So let's begin with a statement that I like to make, and that is CEA, or Controlled Environment Agriculture, can grow anything, anywhere, at any time. And that's a challenge, of course. You also could say, can you afford to do it at all those three components as well? But ultimately, you need to look towards a profit, all right, to sell a product which is marketable and can produce a product. But you also need to use your resources wisely. And we've heard about water resources, but energy resources, labor resources, and space use resources as well. As part of my introduction, I'm going to say that I've been working at the Controlled Environment Agriculture Center at the University of Arizona for the past 21 years. I arrived in 2000. The center was created or established to begin its development in 1998. It has been growing ever since and developing with this vision in mind, as you see here. CEA, that's what our focus is about: sustainability, a sustainable agricultural option, and we look to economic, environmental, and social sustainability. I will give you a little bit of background in this text, in the slides, of how did we get here, meaning how did controlled environment agriculture reach this point? What are some of the recent developments of technology and experiences and understanding in the commercial industry? And I'm going to leave these next three slides for you to review. I hope you have that opportunity afterwards. I begin with the 1970s and up to present, and I say that's the most the recent, the modern greenhouse, high technological facility for producing crops began in late 60s and early 70s. And a big part of that was that hydroponics became more prevalent, more capable, particularly the nutrient film technique. And that progressed through the decades. Energy conservation, certainly in the 80s, in the 90s, computer control and better IPM, and the larger scale facilities that occurred in the U.S. I would say that was the 1990s when the U.S. became more interested in tomato and lettuce production on the large scale, and continued to grow well into the 2000s and until today in greenhouses using sunlight. This continues certainly through this past decade with renewable energy, and maybe the biggest, the vertical farm in 2010, urban agriculture in the interest of food production, grown their products locally for better quality and more dependability and less transportation. So the question and the opportunity I leave for you is, where is this going in the 20s? And it's you who are here to learn, to listen, to provide and share your experiences that will carry this much further through the rest of this century. I do want to stress a couple of things about how I've used hydroponics. As an engineer, as a horticulturalist, I really appreciate the possibility of using hydroponics in a controlled environment to direct the plant to produce as we wish it would produce, when it will produce, and of a quality that is expected. In my first 20 years at Rutgers University, I did a lot of work with tomatoes, the single truss tomato and movable tomatoes, all towards labor savings, automation, and mechanization. In the recent 20 years at the University of Arizona, I'm going to show these three examples of using the controlled environment to produce in very unique situations food production, and also hope begin to show how this would be important for agriculture on Earth and in all over the Earth. The nutrient film technique was used at the South Pole Food Growth Chamber, and this was in 2002. It was installed at the research facilities at the South Pole and Antarctica using a recirculating NFT hydroponic system, as well as a deep water culture and high pressure sodium electrical lighting, because that was what was available and dependable. The technique was used to produce leafy greens, like you see lettuce, in very short rows, 3-foot rows, about 1 meter long, to in NFT situations, where we could change row spacing, and we could have troughs that were fixed at an upper level. We had troughs that would move from left to right at the lower level, so that we didn't waste walkway space when we left. The entire floor or the entire surface, lower surface of the room, the growth room, was bathed by the lights overhead, all ultimately intercepting green leaves. And deep water culture for the tall crops, the tomato, cucumber, sweet pepper, growing in the middle of the room. And this was a mirror image on both sides of this walkway at the chamber. It's still in operation today. Because of these reasons. There's many scientists that are isolated for 10 months of the year that wanted to have fresh vegetables, and we're able to not only demonstrate but develop this usable system that's still in operation to demonstrate hydroponics in controlled environments. Taking it a little step further away from the real world, if we will, the Mars lunar greenhouse still being studied. This says at 2017, that's when I stopped doing much of my work on it. But you can see it's a cylindrical structure, very NASA-like in terms of its geometry. And that's what it is. It's basically a controlled environment growing plants using artificial electrical lights in a hydroponic system that fits the geometry of what would be needed on another planet. The water will all have to be recycled for sure to produce food calories for the astronauts, but also the plants will revitalize the atmosphere. Bioregenerative life support is what it's called. Plants will consume the oxygen that the astronauts breathe out and will return in kind oxygen to maintain the production system and the life support for the plants, for the people. Internally, we see that there was a special hydroponic system, a very lightweight cable-supported plastic tube suspended from either end of the Mars lunar greenhouse. But basically, it's a recirculating hydroponic system in electrically lighted growing situation. Here's another view of it in different angles, and essentially many crops were evaluated for their production: tomato, lettuce, strawberry, cucumber, white potato, sweet potato, basil, cowpeas as well in this recirculating system. Some individually alone, and later on 3 or 4 or 5 different crops in the same environment, in the same nutrient solution, none of them perfectly happy, but all of them surviving and producing a variety of products instead of eating only lettuce or only tomatoes. The cable culture just show that you can produce white potatoes in a recirculating nutrient solution. Obviously, strawberries hang down very nice and easily. Tomatoes still have to be strung up. I think it's the white potato that's figured out, put all my energy in the bottom and it doesn't matter if I fall over. Tomato grows up tall, gets heavy with fruit and falls over unless you have it supported. Same with sweet pepper. The last I want to mention is about seed corn. And there was a challenge that was thrown out about 6 years ago now with a phone call that basically said, can you produce seed corn in your greenhouse? And the answer was, of course, yes. We'll give it a try. And after the first crop, maybe not the best, but after numerous tries, we see here ears of corn, 800 kernels, equivalent to what you can get Iowa in the summertime. We could do that year round. This person here is very important for that. He understands how to take care of the plants, and don't underestimate that person ever in your production system. That may be one of the most important people to get your product and your profits. We'll look at this system. It uses ebb and flood hydroponics to produce that crop, and just growing in a soilless coconut core type mix in a pot, one plant per pot, but recirculating the nutrient solution in an ebb and flood fashion so that you grow to maturity and you reduce the amount of water. You increase the amount of crops per year, at least 3 cycles of the crop, possibly more, which then reduces the time to maturity of a final release from 10 years of a new variety to down to 7 or 8 years. In the process, in a controlled environment, space reduction, 7 acres to do it in the new facility that was built afterwards, and they reduced that from 200 acres. In the process, 95% reduction in water use per plant on the average. So you utilize the production system, and particularly the nutrient delivery production system, to match the needs of your crop. In this case, these benches were fixed. We'll look at we'll look at ebb and flood systems that could be transportable as well. At this point, I just want to take a step back and outline the commonality among all hydroponic systems. And I certainly believe that it does not matter which hydroponic or nutrient delivery system you use. All of them should be able to grow your crop. The question is, will one procedure or type of system be more appropriate, easier, less labor, not more efficient necessarily, but more effective towards the quality of the crop that you're looking for? So you go into a hydroponic system, there's no soil, or there's very little substrate, and that's a benefit in many ways, less expense. But then you lose the ability of the roots and the root zone to support the crop. So in many ways, if it's not a little head of lettuce, or if it's not microgreens that can just stand up on their own, if it's a tomato crop or a sweet pepper or a cucumber, you will be putting string or some kind of crop support to keep that above and protecting the products that you're trying to prepare for harvest. The root zone is the key in the hydroponic system. It needs to be contained. You need to protect the roots from direct sunlight, although many can tolerate it, but it's the lower humidity in the air that becomes a challenge for the roots that will die back. So we want to keep them contained so that the solar radiation is off. We try to deflect as best we can the high air temperatures. We want to keep the light out because also algae will begin to grow, of course, and your root zone will turn green in the presence of light because of the nutrients in the water. But we also want to contain also to keep contaminants out of the root zone, keeping in mind that sometimes the roots are your product, not necessarily the aerial portion. So we have to keep that in mind as well. Distribution of nutrients, and I'm going to talk a lot about this in this presentation, is how to provide and distribute the macro and micro elements, the food, the plant food, that needs to be provided through the water and pumped to the root zone of the plant. And it could be done in many of the hydroponic ways that we've come to know by name, but essentially it's spraying water, dripping water, flowing water, or flooding water, fundamentally. Root aeration. Dissolved oxygen could be considered another nutrient, although we don't always think of it that way. That has to be in the water solution. It's not the air, oxygen in the air, but it's the oxygen dissolved in the water that needs to be provided to the root zone and to the root mass of the plant. So we can do it, help the water to maintain its dissolved oxygen content, by the way, which is a function of its temperature. And the warmer the water gets, the lesser amount of dissolved oxygen is available for the roots of the plant. So we want to maintain that root zone below some critical temperature value depending on the crop. Flowing water will help with improving the dissolved oxygen. Waterfalls and splashing along the way, just letting the flow of the water cause that to happen, can help oxygenate the water. Or you can do an ancillary system of pumping air through air stones, air pumping, or venturis. Or like in an ebb and flood system, you raise and lower the water level, which forces air out of the air pockets of the root zone. And then as the water recedes, it sucks fresh air back in. This is also benefited from top drip irrigation systems, which have worked very well. Maybe one of the most common hydroponic systems, sometimes not even considered hydroponics. but I consider it hydroponics because all of the nutrients are being provided by the water, the irrigation procedure. So dripping from the top allows the drainage to go through the pot, and it brings in fresh oxygen and water and nutrients. And then the environmental conditions, both of the root zone, but now the aerial environment that's available because of the greenhouse that you put on top of it, or the grow room, or the vertical farm with the multi-level using only electrical lighting. Those are just different ways to provide different amounts and different capabilities and maybe quality of environmental control. We do want to limit plant stress and keep them growing and functioning very effectively. The nutrient solution, okay, of the nutrient delivery system, we speak and look mostly at the water and the fertilizer nutrients that are dissolved in the water that then need to be delivered, such as in this image here, by drippers to each plant, in this case, in a rock wool cube, sitting on a rock wool slab and lined up in a row of tomatoes. The question is, where does the nutrient come from? The liquid could be pre-mixed with the fertilizer and stored. Put it in a tank, and when you're ready to irrigate, you pump from that tank. Or on demand, the water can be mixed with the nutrients, and that's typically done in a lower cost, non-recycling situation. Usually we want to have the plants and the nutrients coming from the plants that are not being used to be collected, to be stored and revitalized for further irrigation. The question that we'll get to is, should the storage tank be above or below grade? And that depends on your system design. Then you need pumping power and basically plumbing that can get the water with the nutrients to each plant via a dripper on each plant, or to each row of plants where there's a dripper or an outlet at the beginning of a trough, and the water can flow down the trough and meet up with every plant down that row from one dripper or one opening. Or benches of plants where you have a two-dimensional rows in two directions on a bench, where you have a large inlet like in ebb and flood where it fills and it also drains away and returns back to storage as collected. Finally, you can have the entire floor of the greenhouse, which is covered with a crop in both directions, and you flood the entire floor at some inlet or multiple inlets. We'll see pictures of that as I go further. And then you drain the water, return it back to storage, and prepare for further use of that water. The drain return system has to collect all the drained water. Should not be in a situation where we're doing drain to waste and the water leaves the greenhouse not being used and not being properly cared for. Usually returned to storage under covered channels or in some piping system. And that's why it's nice if the storage tank can be below grade, because then all the water can return by gravity flow and there's no need for additional pumping. Should that system be above the storage, then you have to have a secondary collection tank and then a pumping to the final storage. And then finally, the controls and monitors, sensors that can evaluate the nutrient solution and then change settings as needed relative to the set points required. Monitoring the temperature of the water, the dissolved oxygen of the water, and for fertigation, the pH and the electrical conductivity of the water. I'm defining fertigation here as creating the nutrient formulation, that is the distribution of all the plant food nutrient elements in your nutrient solution. And they are created by concentrated stock solutions, which are then distributed into the nutrients, the water, to create the nutrient solution and deliver it to the plants. Two ways that will focus on fertigation. One, a standard tried and true mechanical proportioners. Example here, Dosmatic or Dosatron injector systems that take the stock concentrates, and as the water flows through the injector, it pumps at a certain proportional rate the stock solution into the water flowing to get a fixed proportion, a 1 to 50, a 1 to 100, meaning that for every 100 gallons of water flowing through that injector, 1 gallon of the stock solution is uniformly mixed in that water and then sent out to the plants. The proportioner mechanical usually operates on each irrigation cycle, meaning it's creating on demand the nutrients put into the water to feed the plant every time the dripper is calling or the timer is calling for irrigation. And that's why drip irrigations are used very much with these mechanical proportioners, but not always, and not into the future necessarily as much as the past with these digital monitoring injectors. And we'll look at some complex systems, and I'll break them down for you because they have some really neat advantages. They essentially do the same as the proportioners. They take stock solution and they put it into a mixture to create nutrient in a storage tank. And simultaneously, it's measuring the pH and the electrical conductivity and the temperature of the nutrient water in that storage tank, and giving you this readout constantly about how they are relative to the set points that you desire. There is a small pump, several small pumps that basically take the stock solution and move it from a small container and put it and mix it thoroughly into the nutrient storage tank, which is done continuously so that the measurements can be done continuously, and you can watch the change in temperature of your nutrient solution in the stock tank, and you can watch the change of pH and electrical conductivity, which occurs over time. Here's a picture of the mechanical proportioner. There's 3 of them in this system, and they represent tank A, tank B, and a tank of acid. So this first proportioner, you see the flow of water coming from the tap water in through the system, reaching the first proportioner. The acid, nitric acid or phosphoric acid, or maybe even sulfuric acid, is used to temper the pH, lower that pH. In Arizona, our water is upper 7s, almost 8 pH, very basic, so we have to add lots of acid. Tanks A and B represent 2 different strong concentrations of tank B, the macronutrients and the micronutrients. Tank A carefully selecting out the calcium and the iron from tank B and dissolving them separately at these high concentrations. If you were to combine tank A with tank B, certainly over 50 ratio 50 to 1. When you get up to 100, you'll get particles forming in the bottom of your tank. There's a reaction, chemical reaction going on with the elements. So you separate the calcium and the iron, inject them in separately at a very low rate compared to, and also tank B at a very low rate, and have them mix before they go out to the nutrient solution in the drip irrigation system. So this system is relatively low cost. It's tried and true. You fix the adjustment here on each one of these injectors, and you walk away from it. And whenever the water flows, at whatever rate it flows, from a low rate to a maximum allowable by the injector, you will get that proportion of the nutrients and the formulation that you want for your crops. An alternative, and obviously a little bit more complex here, is this digital monitoring. Here's a nutrient storage tank. Off to the left, the silver tank. Here, the nutrient stock solution. You could call it the A tank, the B tank, and the acid tank. And here is the fertigation controller and injector system. We'll look at that in detail in the next slide. But what I want to show here is there's two important pumps. The distribution pump is the one when the timer turns on and it's time to irrigate. This one turns on and pumps the water out to all your crops, each individual dripper per plant, or at the beginning of each row, or to the ebb and flood system. And it takes the water from the nutrient storage tank, which has been prepared in advance by the fertigation controller and by this mixing pump, which is constantly circulating the water through the tank and near to the sensors that the fertigator uses to monitor the pH and the EC. So that's the combination now of the fertigation system that's digitally controlled. And here's what I just said. Basically, the small monitoring computer adjusts the EC and pH based on what the grower expects and injects the ejects with the peristaltic pumps the concentrate and stirs that around to maintain the EC and the pH. Then the time clock says it's time to irrigate, so that pump, the larger one, then takes water from the storage tank, delivers it to the plants. Once that is all finished, as the water level drops, fresh water has to be added. That's tap water, makeup water to the system. And then, of course, the pH will change because of our water pH, and the EC will change because the EC of the water is very low. So therefore, the injector system will work very hard after that irrigation to bring it back up to set point temperatures. The beauty of this digital system is that it can give you alarms about situations where you have a water problem, availability, or you're out of range significantly for your pH or your conductivity, and even the temperature of the water in the solution. Here is a close-up of that fertigation controller. There is a monitor that has a small display that you can set your set points very clearly and easily, and it tells you what the set points are and what the current readings are, because its sensors are right behind this board in the tank, the nutrient storage tank. Here it is without the lid on it. You can see the reflection of the water. So that tank is being stirred and added pH, acid, the A solution and the B solution by these peristaltic pumps, which are pumping out of, in this case, 5-gallon buckets, not those 30-gallon stock tanks. Same 50-to-1 ratio or 100-to-1 ratio, and the same nutrient formulation. You can choose your favorite. I'm not going to go there because that's a discussion all on its own about what's the best one, particularly for the type of crop, the species, and the age of the crop. So I'll just say, use your favorite, get an A tank, get your B tank, get your acid, and allow these pumps to pump out and into the nutrient storage tank, and allow this controller to maintain the values that you set and you want to deliver to your plants, and then allow the irrigation timer to irrigate and deliver to the plants. Okay, that's enough background at this point. I'm going to look at specific nutrient delivery by name, nutrient film technique, ebb and flood, deep water culture, drip. Let's look at that and discuss about them, and why I think it's interesting to know about all of them when you're making your decision about how you're going to grow your crop, because it should depend on your crop. It should depend on your experiences with that crop. Never start a new growing system with a whole new greenhouse. Get some experience on a small scale before you transition to a new way. You'll appreciate that when you reach your time when there's a failure because of a lack of experience. But here we are, nutrient film technique. And here's the graduate student working very hard in here to take care of these plants to be transplanted. These are the channels. We'll look at more detail. There's the nutrient storage tank. And here is that fertigation system that we just looked at. Here we are, the nutrient storage tank with the submersible pump. The time clock turns that on. It pumps the water out to the far end of each of the troughs. The troughs have a slight slope, 1 to 2%, and the water returns after a few minutes, all of it, to the nutrient drain and then back into the storage tank. These troughs happen to be 20 feet long, 1 foot wide, and 2 inches deep, because we were growing cherry tomatoes, and they would fill up this entire 4 foot wide space with a small little cherry tomato bush. You might have narrower troughs for lettuce, about half 6 inches or 4 inches wide, and there's many of them that are commercially available, certainly. Here are the EC and pH sensors that are being bathed in the nutrient storage water tank from a small circulation pump that is in the tank or adjacent to the tank, and then sending the signals back to the fertigator to determine about set point. Flow rates are on the order of 1 to 2 liters per minute per channel. A liter is about a quarter of a gallon approximately. And this is going to depend on the crop and the age of the crop. I usually like to run it continuous NFT, which is not usually expected to, when you newly transplant, because you want those roots to get out of the cell, like a rock wool cube that you've planted, or a potted little pot, that you want the roots to come out and enter in the entire width of that trough and begin filling it up. So a few days of continuous pumping, and then go to a 5 minutes on cycle with a 25-minute off cycle. So basically every 30 minutes, twice an hour, you're giving them 5 minutes of irrigation. And then maybe change that to a more frequent time as the plants get older, and as depending on the time of year, of course. The big view of the entire greenhouse. These are 3 separate research systems, but basically I put it together this way because with a storage tank, a couple of troughs, and this board of a fertigator here with some 5-gallon buckets, you've got a self-contained recirculating hydroponic nutrient film technique system that is very dependable. All right, let's go to the top drip irrigation. Not much to show here, except you have a tube, irrigation pipe with the drippers coming off, micro drippers coming off, and then the orifice here to drip the water to each of the plants directly in the row, ultimately creating very large plants here nearing first harvest, with the capability of going 11 or 12 months throughout the year with a continuous tomato crop, harvesting on the order of 1 to 1.5 pounds per truss per week per plant. And in here, we recommend, in the warm area in particular, small volumes of watering done many times more frequently. 60 milliliters to 100 milliliters, 3 to 4 ounces of water per event, 1 to 5 times per hour, depending on the age of the plant and depending on the time of year. What this does, of course, it brings fresh water, but also more dissolved oxygen into the root zone. In this case, it's rock wool, and it drains away root materials, exudates, and this is a trough that you can purchase that can be elevated or can sit on the ground, that collects all the drainage water left over from the irrigation of the plant. Here's the ebb and flood system, close up now, that seed corn developing system, a fixed tray, 4 foot by 8 foot, inlet water coming from the nutrient storage tank was at the far end of the greenhouse, and return water draining back to the nutrient storage tank to be used by other plants. Ebb and flood made a lot of sense for this system because I knew that the client, the people that are going to use this, wanted to automate their system, and they wanted to put these crops on transportable benches. And the beauty of ebb and flood is that the inlet drain and the outlet drains do not have to be directly connected to the bench, meaning that there's no plumbing disconnect you have to do. Whenever you want to move the bench, you can, unless you're in the middle of an irrigation, which makes for transport much, much easier, and therefore ebb and flood on transportable tables or trays. But they can be on fixed benches, and they can be on multi-level frameworks, but we don't want to irrigate to too great of depth because of the weight. It also can be on concrete floors. I'll show you a picture of that shortly. But plants can be grown in individual pots or in rock wool substrate as individual units directly on the floor, directly in the tray, or on the transportable bench. The goal is to flood to a shallow depth of only 1 to 2 inches, even if the rock wool cube is 3 or 4 inches tall. The idea is to have the water come up from below 1 to 3 times per day, depending on the age of the plant, and drain quickly. We want a return water, fill that tray in 10 to 15 minutes and drain in 5 to 10 minutes. So a relatively quick cycle, and have the water return back to the storage tank to be used in the next cycle, or in the next bench, or the next bay, for example. The idea is to have fewer, not long duration floods. That's just not good. You want to have quick draining and do it more frequently. You have to choose your substrate carefully. 10% air volume in the substrate, very friable, lots of pore space so that it fills up quickly. It also drains quickly, and at saturation, it loses its water more quickly. So you're irrigating again, bringing in more dissolved oxygen. Here is what I've been discussing, that the rise and fall of the water expels gases that are in there and dilutes organic material that's in there. It also brings in fresh air as the water drains away. Deep water culture or floating raft. Here you see a series of the students in a 4 by 8 foot insulated deep water culture system, and a close-up of the beautiful white roots for the lettuce grown in this, making harvest as easy as how big of a tray can you pick up. That's what it really says here. That's how it determines how big these modules can be, the maximum size. You see the good uniformity of growth in this system. Operations are to fill the tank with nutrient solution on day 1 to a depth of, we use 12 inches. Because of our excessive amount of heat in Arizona, we can grow this lettuce through our summer period when, even with our evaporative cooling, we cannot reduce the air temperature in this greenhouse to less than 85 degrees peak temperature. Now in the night, we do get cooling, so we can get it down in the 70s, at least Fahrenheit. But the water temperature never goes above 75 degrees Fahrenheit. And that's because of these insulated containers. And if we have to, we can cool. These were not being cooled. They grew a 30-day crop with no refill. The floating bed or tray stayed at its position and wasn't floating anymore as the water level dropped, but the air gap formed. The roots went down into the nutrient solution, and the plants were harvested in good quality. If you go to a lesser volume of water, there's a question of, will you need refill? Probably. And maybe you have to do aeration by air stone, which is a possibility. because of the lesser volume of water and the less stored dissolved oxygen in a 30-day crop. But if you have a quicker turnover crop, then that may not be a problem. If you have a longer crop, then for sure you're going to have to be adding oxygen, dissolved oxygen somehow, and probably adding more nutrient water. Here is a commercial demonstration of a hydroponic system for lettuce and their harvest. You see the mature plants here that were harvested. Here's the water that remains. The less mature plants were way in the back. And here we have Debbie May demonstrating the tray, the size that they were using there, and the roots in the deep water culture. This was near Yuma, Arizona, in the summer. I estimated the air temperature outside the greenhouse was over 105 degrees Fahrenheit. And that's not an unusual day, but yet you can see how this deep water culture, keeping the root zone cool, can produce relatively good quality lettuce even through the summer. Aeroponics, and I see my time is moving quickly here. Aeroponics, spraying water basically. And in this case, Dr. Hayden was interested in the roots, not in the aerial portion of the plant, for medicinal purposes. This happened to be burdock, and here we are in the, you see the large leaves in this aeroponic system. And here it is before it was transplanted and finished. Here's the engineer demonstrating the framework that he built out of PVC, nutrient storage tank, pump outside the tank going to spray nozzles, and the wings, the gull wings on the top of the A-frame is covered with poultry netting, chicken wire that we would cut slices through the white plastic through into the chicken wire with the 1-inch rock wool cube and start the seedlings at relatively high density, and all the roots would be sprayed from underneath. And there's Dr. Hayden on the other side. She harvests the roots because she needs that material for the phytochemicals, and then prunes off some of the leaves and doesn't kill the plant. That was the goal of the aeroponic system. So a very specialized system and somewhat challenging and expensive to operate and run, but it served its purpose. Clean roots, no soils, good phytochemicals. And just a picture of, here's stinging nettles, another project that she had, biomass gone crazy for sure. That's a challenge with aeroponics, is controlling the growth. Another topic was this ginger. And here she created an aeroponic system with sort of a hydroponic system and then the green part of the plant. So she wanted the green plant, she wanted the roots in the aeroponics, but of course we all want the ginger that was in between. And here it is, very clean system. Maybe not the most practical way to do it, but certainly demonstrating that you could grow almost anything in a hydroponic system. Here is a very unusual shaped radish. And I show that mostly because how many of you out there believed that you had to grow root crops in the ground because they needed the pressure of the soil around them to grow and produce the tuber or reduce the root? Wrong. This is an aeroponic radish. There they are sitting on top of an aeroponic system inside of a growth room where the tank of nutrients would be underneath, the nozzles would be above, and the roots would be hanging down below. We're now looking up from the nozzles to the rock wool cube with these stunted roots. And this was some work that I was doing for NASA. They, and of course others would say, we're not eating the roots. Can you do something to produce a good radish or a good crop, but not make roots? And that's what you do. You stunt them. Only irrigate once every 180 minutes, and you get no roots, and you get a similar size radish or lettuce. We did both. If you go back down to a 30-minute cycle time, we were in a growth chamber, so be careful here at doing this in a greenhouse. But with the shorter cycle times, we would get a lot of roots, which was not necessary. You can't eat the roots. Long term, you can change things in aeroponics. All right, finally, storage situation. Those who are building a system will need some of this information. I'm not going to go in detail. It's here to say, how big of a storage volume do I need? And basically somewhere between 1/2 to 3/4 of a liter per plant for large plants like tomato, cucumber, pepper, or only 1/4 of a liter to 1/2 a liter per plant for leafy greens. So the smaller your storage tank, less expensive. The larger your storage tank, the more buffer you have, the more time you have to remake new water, particularly if there's a problem. So depending on how risky you want to take, you can vary the size of your storage, save some money, but maybe save some sleep too by making a larger one. And here's the question of, if you can, put your storage below grade. It's cooler, it's in the dark, it's out of the way, and you can use gravity flow. If you can't, you have to be above grade, then insulate that storage tank as best you can, and be careful about pumping the water that you collect from gravity flow from each of your systems to have to pump it up into the nutrient storage tank. We'll look to pumping capacities. It's going to depend on your system, how big it is, how many, whether you're using ebb and flood, whether you're using drip irrigation. So I'm not going to go into that, except maybe to say here, think about the weight of the water that you're putting into your system. It's 7.5 gallons it's 7.5 pounds, 7.5 gallons in the system is 750 gallons, but it's 8.3 pounds per gallon, which if you're going to suspend that somehow or hold that up in the air, that's 10 trays weighing over 6,000 pounds. Think about that. That's a challenge when you're doing these systems, and particularly when you go to vertical farming. Vertical farming, indoor, multiple level, electrically lighted only, no sunlight, that you have these trays in multiple levels that need to be supported, that need to be moved, that need to hold water. Do it in the least amount of volume of water as possible, as opposed to greenhouses where you can use hydroponic systems that we've been talking about. But this is the new. Everybody is interested in vertical farms, believing that they are the highest technology. And I would say they are just as high technology as a greenhouse using sunlight. They do have some increased water use efficiency. It's been stated a little bit here today. They do work well in their extreme climate conditions under limited space conditions. Very, very hot regions of the world, the Middle East, for example, very, very cold regions of the world, the Antarctic or the Arctic, or the place where space is very, very valuable in major cities, for example. But you have to watch out for your electrical costs, for lighting and for HVAC. That's climate control, cooling, and dehumidification. It all adds to the kilowatt hours that you need for growing, producing that crop. And I like to compare and ask people, what is your production in edible grams or pounds of edible product per kilowatt hour? Because that tells me how effective that they really are in producing their crop. Takeaways, I'm going to leave these here as definitions. We went over these different types of hydroponics. You should be able to recognize the difference and maybe even a little bit of the value of why you choose one over the other. And the same, and I like that introduction, Genoa, for the greenhouse, the high tunnel, and the plant factory. Why you choose one over the other? Because there are benefits to each. A lot of the benefits have to do with experience. Final thoughts. And there's two things I have to say here. This I'll just read. Successful food systems will be achieved by the fundamentals, understanding and implementing CEA and hydroponics for environmental control in a protected facility with flexible design, plant monitoring, automation for labor savings, and, very important, experienced growers and producers. And I say, and someday from Martians too, when they're growing on Mars. And I look forward to that in the near future. Things are really looking up for that. But the final thought is education. So I have to show you this slide. I think many of you at A&M recognize this young man here, Dr. Hooks, and we're so glad to have him at the University of Arizona. And here he is, after being here only a few weeks, is doing a hydroponic tomato intensive workshop in January, the 7th, the 8th, and the 9th. I believe it's Friday, Saturday, Sunday for you weekend warriors as well. Come on out. It's online or it's on site. On site, you get the hands-on. We'll get your fingers a little bit of green with the tomatoes in his greenhouse. He needs all the help he can get taking care of those plants because the students are gone. So you guys got to help us out there. But in the process, you'll learn about all of these things as described here. Hands-on, face-to-face, if you can. We'd love to have you here. We're looking forward to it. And we focus on the intensive workshops where it's just growing tomatoes. We have other workshops or the short course, which is more general. Yes, we use tomatoes as example, but in March 7th, 8th, and 9th, we're having our 21st annual greenhouse crop production and engineering design that go together to have a good crop, good quality, and good production, and creating good growers. So having said all that, I really have to be quiet. I'd love to answer questions in any way possible. Come on back, Joe. What can we do now?
Well, we have.
Do I have to return?
Yes. Close the share screen, I guess.
No.